In 1956, 10 scientists gathered for a summer workshop. They believed that by September, they would have cracked the code of intelligence. 70 years later, we're still making the same promise. Every decade, a new machine appears, and we declare, this time, it's real. So here's the question this video will answer. Does the history of artificial intelligence reveal that we're closer than ever to true machine thought? Or does it expose a pattern we refuse to see? By the end, you won't just understand AI's past. You'll recognize something uncomfortable about us. This is episode 3 of the AI Saga. In episode 1, we explored Alan Turing's original question. Not whether machines can think, but how we would ever know if they did. In episode 2, we examined cybernetics and the feedback loops it created, the patterns that began integrating human and machine long before AI promised to replace us. Today, we trace what happened when those foundations met ambition. We'll move through 6 distinct periods, from theoretical ideas before computers existed, through cycles of wild optimism and crushing disappointment, all the way to ChatGPT and the promises being made right now. But this isn't just a history lesson, it's a mirror. Because every time AI advanced, we saw intelligence. And every time it failed, we blamed the machine, never the assumption. Before there were computers, there was a question. In 1936, Alan Turing published a paper that would become the foundation of everything we now call computing. He described an imaginary device, a universal machine, capable of executing any logical operation, given the right instructions. Soon after, physical computers began to exist, massive room-filling monsters of vacuum tubes and wires. But Turing wasn't satisfied. In 1950, he asked the question that still haunts us. Can machines think? He said the question itself was too vague. The words were empty, so he flipped it around. Instead of asking what machines are, he asked, how would you know if they were? The problem was philosophical, not technical. We never defined what intelligence actually is. We only agreed to observe behavior. 6 years later, the field was officially born. At Dartmouth College, John McCarthy coined the term artificial intelligence. The founding document declared that every aspect of learning could be so precisely described that a machine could simulate it. They believed a single summer would be enough. And for a while, it seemed possible. The logic theorists proved mathematical theorems from Principia Mathematica, some more elegantly than the human originals. ELIZA, created by Joseph Weizenbaum in 1966, simulated a psychotherapist using simple pattern matching. People poured their secrets into it. They preferred the machine to real therapists. Herbert Simon predicted that within 20 years, machines would do any work a human could do. But there was a hidden problem. Real-world tasks didn't behave like logic puzzles. They exploded into trillions of possible combinations. Translation systems made laughably bad mistakes. The problem wasn't stupidity. Language simply isn't logical. The machines worked in laboratories. The world was not a laboratory. This is where the dream began to crack. In 1969, Marvin Minsky and Seymour Papert published perceptrons, a mathematical proof that early neural networks couldn't solve even basic logical problems. The XOR function, something a child could grasp, was beyond their reach. Funding for neural network research vanished almost overnight. Then came the institutional verdict. In 1973, the British government commissioned Sir James Lighthill to evaluate the state of AI. His conclusion was devastating. Nowhere in the field had discoveries produced the promised impact. The UK cut funding to nearly all AI research. The first AI winter had begun. But the field didn't die. It adapted by shrinking its ambitions. Instead of general intelligence, researchers built expert systems, narrow programs that encoded human knowledge as if-then rules. Migan diagnosed blood infections using 450 hand-coded rules. It performed as well as junior doctors. Xcon configured computer orders for Digital Equipment Corporation, saving $40 million a year. These systems worked, but only inside their boxes. Every rule had to be programmed manually. Every assumption had to be perfect. Step outside the defined domain, and the system produced nonsense. Geoffrey Hinton was one of those researchers, trying to keep neural networks alive while the entire field decided they were a dead end. He couldn't even publish papers mentioning neural networks without them being rejected. The field had decided this path is over, but Hinton didn't listen. What looked like intelligence was expensive, fragile automation. By 1987, cheaper personal computers made specialized AI hardware obsolete. The second AI winter arrived, and the question lingered, was this intelligence or just very elaborate programming? While the world forgot about AI, something was changing. In 1986, Geoffrey Hinton and colleagues made backpropagation practical for deep networks, a technique that had been theoretically known but never successfully applied to multi-layer networks until then. But the real shift wasn't algorithmic, it was philosophical. In 1997, IBM's Deep Blue defeated Garry Kasparov at chess. Kasparov later described feeling a dangerous intelligence across the board. But here's what's important. Deep Blue didn't understand chess. It calculated 200 million positions per second, futures no human brain could ever navigate. Kasparov felt intelligence, but what he encountered was optimization. The machine didn't think like us. It was doing something we couldn't track. And that was a different kind of intelligence, if you could call it that. Between 1997 and 2011, IBM proved this pattern again and again. Watson won Jeopardy using statistical pattern matching, not reasoning. Deep Blue Watson. They were not minds. They were computation at scales that exceeded human capacity. And then in 2012, that pattern exploded into something new. A team led by Geoffrey Hinton entered the ImageNet competition with a deep neural network called AlexNet. It achieved an error rate of 15.3%. The next best competitor, 26.2%. The gap was so large that the entire field pivoted overnight. No one had predicted this. The algorithm, backpropagation, had existed since 1986. The hardware, GPS, originally designed for video games, had been improving for years. The data, 15 million labeled images from ImageNet, had been painstakingly assembled by Fei Li using crowdsourced labor. None of these elements were new, but their convergence was. In 2016, AlphaGo defeated Lee Sedol at Go, a game with more possible positions than atoms in the observable universe. Move 37 in the second game defied millennia of human intuition. Experts thought it was a mistake. It won the match. In 2017, Google published Attention is All You Need, introducing the transformer. Here's the insight. Instead of processing language word by word like a slow reader, the transformer could focus on what mattered across an entire text at once. You could train models on incomprehensibly vast amounts of data. Language processing, and soon everything else, changed. The machines weren't thinking, but they were doing things we couldn't explain. And then something shifted. The lines between human and machine started to blur. In 2017 and beyond, the world noticed. GPT-3 launched in 2020 with 175 billion parameters, trained on 45 terabytes of text. It could write poetry, generate code, compose essays, tasks it was never explicitly taught. In November 2022, ChatGPT reached 100 million users in 2 months, the fastest adoption in technological history. And everyone believed, the machine speaks like us, therefore we assume it thinks like us. But ChatGPT doesn't understand anything. It predicts the next word, billions of times, probabilistically. Fluency creates the illusion of comprehension. We see intention where there is only statistics. I work with these tools daily, and I face the same frustrations you do. Outputs promise brilliance, but fall short of benchmarks. Not sentience, just computation at scale. And here's the uncomfortable truth. Consider Google Bard. In early 2023, the company launched it publicly with an advertisement. Live demo. Billions watching. Bard made a single factual error. It claimed the James Webb Space Telescope was the first to photograph an exoplanet. It wasn't. Google's market cap plummeted by nearly $100 billion in the days following. Not because the error was catastrophic, but because everyone realized this thing that sounds so intelligent hallucinates facts with total confidence. It doesn't know what's true. It just predicts what's likely. And this isn't unique to Bard. Even Claude, trained by researchers focused on safety, succeeds only 60% on short tasks, 45% on complex ones. The pattern is the same: convincing fluency, brittle performance. The illusion is always the same. We see a machine speaking fluently and we project thinking onto it. We are living the exact same cycle as 1956. The only difference? The machines are more convincing now. Promise, limited success, failure to generalize, disenchantment, quiet improvement, convergence, resurgence, and then back to promise. So does the history of A. I show we're still far from superintelligence? The answer is yes, but not for the reasons most people think. The problem isn't that machines are slow. It's that we never answered Turing's original question. We never defined what thinking is. We just kept building machines that imitate it better. Every cycle reveals the same truth. We project intelligence onto behavior we can't explain. And when we explain it, we stop calling it intelligent. It's as if intelligence is just another name for the things we don't yet understand about our own minds. This series was never really about AI. It was about us, about why we keep believing that the next version will be the one, about what it says that we want so badly to create something that thinks. In the next episode, we'll pause the history and ask a different question. If these machines aren't truly intelligent, what exactly are they? We'll define what different kinds of AI can and cannot do. Because clarity about what something is might be more important than speculation about what it could become. If this exploration resonates with you, if you want to keep questioning what intelligence really means, consider subscribing. A like or share helps this reach others asking the same questions. The books and references that shape this episode are in the description. This video is part of the AI Saga, Science, Soul, and Silicon. New videos every week. Because at Tender Reason, we take reflections seriously, even when the subject keeps promising more than it delivers.